So first off, who is the Agricultural Research Service? So I get this question a lot. It's like, oh, I work for the USDA. And they're like, oh, so beef. I'm like, no. We're actually USDA's chief scientific in-house research agency. So we're really focused on finding applied solutions to agricultural problems. So we have over 90 locations all across the US, 2,000 plus scientists and postdocs. Most of them do focus on ag stuff, so a lot of genetics, crop use, irrigation, things like that. But there are actually 2 locations that are on watershed science. So one of them's in Arizona, and then one of them is here in Boise, Idaho. And so we're also the only unit that does snow hydrology. So I think it's pretty neat that the only part of ARS that does snow hydrology is located in Idaho. So we run an experimental watershed called Reynolds Creek Experimental Watershed. It's in the Oahes. So this is a long-term monitoring and research basin. So we've been running it since 1960. So it's pretty small. It's about 240 square kilometers, 90 square miles. So when they started it, they installed 81 precip stations. So basically 1 per square mile. They probably thought the maintenance was too much, so they pared that down quite a bit. And so currently we have 32 climate stations, 36 precip sites, 7 eddy covariance towers. So this is measuring carbon fluxes, and turbulent transfer at really high resolution. 14 weirs for streamflow, soil moistures, and 3 really instrumented headwater basins. And one of them is a snow watershed. And so that's where we do a lot of our research and development on the modeling and techniques that we use. So I always like digging through our old photos because we have a lot of really neat old instruments. Some of these are still in use, but a lot of them aren't. So, you got your temp. The middle one's solar radiation. So, they've come a long way to make it a lot smaller. The wind gauges, everything used to be recorded on tape. So yeah, we do a lot of measurement of precip. So here was about 11 precip sites, all condensed into one. So it's kind of really neat seeing how they're kind of trying to figure out how to measure precip in the Oahes. This site doesn't exist anymore, probably because it was just too hard to maintain. I mean, 11's a lot. But so yeah, we do a lot of snow. We do a lot of snow work, measuring precipitation. I think one of the neat things about our watershed is the weirs for streamflow. So these are our 2 main weirs. The one on the left is kind of in our mid, halfway up the catchment, and then the other one in the middle here is at the outlet. And these are these structures you just don't see anymore. I mean, they're kind of engineering feats. They're really neat. And then here on the right is the 1984 flood, and so you can kind of see one of the little guys on the right for scale. I mean, these things are really, really neat to see in action. Anybody know where SNOTEL was first tested? Reynolds, yeah. So this is the first snow pillow. We worked with NRCS back in probably the 70s or 80s, and so this was kind of their first try at the pillows. So they had dudes out there with glasses and poking at things, I guess. So yeah, so this was all done at our instrumented snow site. So we've had a lot of history of doing snow physics, snow measurements, and the likes up at that site. So yeah, we also are part of the World Meteorological Organization, so there's a lot of cool old structures out there for different wind fences and for your different precip cans. So it's really kind of this really cool ancient history of climatological records. So on to what I'm here to talk about. So a little bit about our project, how we're integrating modeling, remote sensing, some of the hydrology applications, and our kind of where our next step is in our operational modeling. So, I mean, snow is important. I don't have to say that to this group, but in a little different context for agriculture and irrigation, snow is really important because it's the nature's reservoir. and water supply system. So the snow stores the winter precip really efficiently, and it releases it slowly during the spring to provide the whole water supply throughout the summer. So when we're kind of done here with avalanches, we're still thinking about it out until August of how that snow is going to come off. We're seeing a lot more demand for the water, and we're also seeing a lot more rain during the winter. So this is meaning that we're needing more sophisticated methods to manage runoff. So we typically, like on your right, this is a typical watershed in the West nowadays. You have your mountains, snowpack flows down into a reservoir that you can then regulate for stream flow. And so without it, does this work? Maybe not. I'll keep pointing. So in blue, we have a typical hydrograph. So we're going to see spring. Perfect, thanks. So I'll see the spring melt pulse in, say, April or May. You get a lot of it all at once, and then it kind of starts tailing off. But with reservoirs and regulation, we can kind of smooth that out, and this is the really important part of having that water later in the season for irrigation and crops. But the demand and the changing climate is really affecting both ecosystems, agriculture and irrigation, power generation, and recreation. So it's a really wide-fetching problem. So operational hydrologic forecasting. So these are typically statistical streamflow forecasts. So they're regression-based that just relate measured SWE at say a pillow to summer streamflow. A lot of this is based on the NRCS SNOTEL network here in the West. We also use temperature index runoff forecasts, but these are, again, calibrated models between air temperature and snowmelt. And so problems arise when the climate's changing, air temperature isn't constant anymore. And so both of these methodologies really assume that the current conditions that we're seeing today, we've seen in the past, and that isn't really happening anymore. So a lot of these methods, you need a lot of data. So 30 to 70 years of data for these models, but they're still not capturing that climate variability. The last 4 years have been a really good example of that. And basically every single year we've set records, it seems like, whether it's drought, floods, temperature, precip. I mean, it's, when we break a record, we're no longer normal. So a lot of these things are starting to fall apart. So this is a really interesting plot. So this is analysis of a water supply forecast in California for the American River. So we have our forecast error versus our probability. So half the time, our forecast errors are 20%, which is a lot. 1 in 5 years, our errors are greater than 40%. So, 1 in 5 years, we're talking 40% of the water could be flowing into your reservoir, or could not be. So that's a huge margin of error. So where we do a lot of our work with water supply in California, they've really kind of pioneered the next step forward. So they're introducing a lot of legislation, a lot of money. So $2.5 billion to build new dams and water supply projects. One we're really interested in is a new bill for $150 million over 10 years. That's going through the Senate right now for water supply forecasting with modeling and remote sensing. So that's really neat because modeling and remote sensing is the project that we're working on. So how do we improve Western water supply forecasting? So we couldn't do it alone, so we partnered up with NASA Jet Propulsion Lab. And so we formed Airborne Snow Observatory. And so through this project, we're kind of serving a whole bunch of different stakeholders from the California Department of Water Resources, NRCS, Reclamation, as well as a slew of irrigation districts, water managers, basically anybody that relies on snow in California. Because this is really important for this last historic 4-year drought from 2013 to 16. Really affect ag and irrigation, power generation, and as well as affected actual municipal conservation, basically rationing of water. So how are we going to integrate this? So we've come a long way. You know, we used to ski out in fedoras and rear entry boots, just taking point measurements. So very standard to what we do when we go out on a tour. We're taking these point measurements, trying to extrapolate that into a spatial context. But now we're in this kind of spatial revolution in the hydrology world. So we have a plane that has a lidar mounted on it, and so the lidar is providing us a measurement, a high-resolution measurement of snow depth. And so with this, we're getting an amazing temporal and spatial resolution of snow depth across entire watersheds. But for hydrology, the holy grail is SWE, and luckily it's an easy equation. So it's just depth times density, and so the plane is measuring the depth. It's measuring at a really high resolution. And so what we need is a model to estimate what the density is. And so the model that we work with is doing that, and so we can combine the two and get SWE across these entire watersheds in California. So this is our team in Boise. So there's 6 of us here, and we've actually added 4 more. So we have a really great, huge team working on this project. So the model we work with is iSnowbow. It's a physically based snow model that does the mass and energy balance of the snowpack. We run this at varying spatial and temporal resolutions. So for the projects here, we run them at 50-meter spatial resolutions and an hourly timescale. So pretty high resolution. The input data that we use for the model used to come from like cooperator measurement network. So this would be like your SNOTEL. This would be the stations that the Sawtooth put in. But now we've kind of switched to move to atmospheric models. It's a little bit more broader. We can apply it more areas. And so we're using a product that's put out by the National Weather Service. So what iSnowbow is just it's a pretty simple 2-layer model. So this isn't your snowpack model that's trying to model every single layer, whether it's faceting, if it's growing a surface hoar. We're just kind of looking at the overall energy balance. And so we break it down into a surface layer and a lower layer. And so, but we're tracking, all the states of the snowpack. We're doing the mass, density, depth, cold content, which is the amount of energy required to bring it up to 0 degrees or melting, as well as the temperature of the snowpack. And so we're solving this at every grid pixel, and we then can basically grid that over these entire watersheds and estimate what the SWE is or the temperature is of the snowpack. The planes, the ASO flights are ran by NASA JPL. What they do is they basically take off. They're based out of Mammoth, and so they take off and just mow. I mean, it looks like me on a Sunday afternoon, but it's they just kind of go back and forth, make a turn, and come back. And so what that gives them is a lidar point cloud. They process it down to a 3-meter digital surface model. So this entire watershed, you're getting a 3-meter measurement of what's on the ground. So we'll go out and fly snow off in the summer, so you get the bare ground, and then snow on in the winter, and then you have snow depth. Sounds simple, but they somehow figure out how to make it pretty hard. So typically turnaround, there's a lot of data involved, so turnaround's about 2 to 5 days, and that's a really unique thing for LiDAR. So typically you're looking for like a month turnaround time. And because the demand is there, that the water managers need this product quickly to make flood control decisions, we're getting this product turned around in a really quick order. So snow depth of 3 meters is really showing you the slope scale at this large watershed size scale. And so the watersheds that we're looking at in California, we're doing 6 main watersheds, basically from the Tuolumne down to the Kings, if you guys are familiar. So south, basically the whole southern Sierras. Interestingly enough, this whole modeling domain is basically the size of the Boise River Basin. So put that into context. But it's really providing you a snapshot of the current snow distribution. So this is just a snapshot from a couple weeks ago in the upper Kings. And so, you know, the range is 0 to 5 meters, and the deepest here in these kind of corner, basically the sloughs, are greater than 12 meters. So we're just seeing this really cool high resolution estimate of what the snow, where the snow is in these watersheds. However, most of these flights, we're really focused on snowmelt. So a lot of them are March and onward. So we're working towards getting a lot of the accumulation phase. So trying to get some January, February, where it would really be applicable to, you know, the avalanche centers and things like that. But a lot of the, you know, the demand is when that snow is going to come into the reservoir. So to merge the two, we basically can take these snow depths and plug them into our model. And so here are 2 examples of that. So this first one here is from 2014. And so this is the Tuolumne River Basin. So this is Hetch Hetchy, and basically the Yosemite National Park is kind of the upper part of this. So these little insets show just kind of a little zoomed in area. So we can see it's pretty smooth for the first, when we get the first flight. Our model is kind of a smooth estimate of what's happening out there. When we update that with the lidar, though, we can see a lot of spatial structures start coming in. And so this is kind of taking into account the wind redistribution, avalanches, you know, different precipitation gradients, all of that. And so we can see where, so this is basically the change in SWE, so we can see where we had an increase in blue or decrease in red. And so you can just kind of see where we have, you know, adding SWE into these drifts or taking it away from the scour on the ridges. So typically the first update is a bigger update because we're kind of relying on how good our inputs are. So this one was a 24% increase. So we were a little low leading up to the first flight. In 2015, this was the 8th flight of the year. And so looking at the model, we already have that spatial structure. We've already kind of set it up from the 7 previous flights. And so when we update it with the 8th flight, the change is a lot less. We still get a little bit of changes. That's for things that we just can't account for in the model. But it's a much smaller absolute change than it is towards the beginning. So it's really important to have a lot of these flights to really kind of keep the model up to speed. So I mean, there's a lot of power when we combine the flights and the models, because the flight basically defines the snow distribution. It's a snapshot of what's on the ground. But the model it's a model, so it's continuous in between the flights. And because it's a model, we can do things to that model to kind of see how the snowpack's going to react. So we've been doing a lot of work with short-term forecasts. We do some things what we're calling history repeats itself. So we get a lot of calls saying, hey, this storm looks a lot like this storm X from 4 years ago. And we're like, yeah, okay, so we can go find that, pull that storm out, plug it into the current snowpack, and basically see how that snowpack's going to react given the future conditions. And so this is really important for a water manager because it tells them how the basin's going to react to this potential future weather. So it'll either say they need to, you know, up their flood releases, or they can kind of go it down. So it's really important information for them. Another thing we found from feedback from stakeholders is really important is that when all the snow pillows melt out, they're basically flying blind because they have no measurements now. But because of the model and the flights, we now have measurements above the measurement stations. And so we can estimate how much is left. And so that's really important for final fill of reservoirs because you want that thing as high as you can before summer hits. And so here on the right, we just have 4 different years. And so this is a combination of, I think there's about 40 lidar flights in here, it's a spectacular data set. And so in red, we show how well the model is doing by itself. It does terrible by itself. R² is 0. It's just didn't even get it. But when we update, when we get these really important flights, we're really doing really well with where the snow is, how it's melting, and providing that good information to the stakeholders. So, kind of moving on to some of the applications. As snow hydrologists, we love a good flood. It just makes things exciting. So we'll kind of go back to 2017, with the snowpocalypse in Idaho. Seeing the rooster tail at Lucky Peak on the Boise and the Arrow Rock spillway being activated for the first time in 11 years. And the Glory Hole on the Oahe Reservoir, that was last used in 2011. I mean, some of these, they're pretty cool to see.
What is the Glory Hole?
So this is the spillway for it. So it basically is a ring, and it's like a bathtub. So when your water gets too high, the water just kind of flows into it. And I think this one drops 500 vertical feet, makes a left turn, and then goes straight out, and just shoots straight out into the Oahe Canyon. So highly recommend to go see it if we get there this year. At Ada, we're taking a tour of it, and there's some pontoon boats up the way, and a pontoon boat got loose and went down it. Nobody was on it, but it got mangled pretty good. It shot out the other side, but yeah, it was crumpled. Yeah, so what led to the flooding? So we had over 200% of average snowpack. It was a huge year. So in the Boise River Basin, they started doing flood releases in mid-February, and they basically finished up in August. And so that's coordinated between Reclamation and U.S. Army Corps of Engineers. So this is the stream flow through town in Boise. So winter started off pretty slow, and then they realized they had a problem, and so they shot it up. And so flood stage in Boise is 7,000 CFS. So they hit that early March, stayed there till mid-June. So we had 3.5 months of flooding between 9,000 and 10,000 CFS through town, which was, it was awesome. It was really cool. And I'm glad I don't own a home on the river, but yeah, it was neat. So another aspect of this is that Lucky Peak, so that's the lower reservoir that recorded its second highest inflow on record at 24,000 CFS. And basically what caused that was a rain on snow event. So the conditions that led up to that was basically an isothermal snowpack. They had about 85 degree Fahrenheit in Boise for the whole previous week, and they got a couple inches of rain on top of that. And so over here on the right is our snow water input, or SWI, so that's rain on bare ground or melt out of the bottom of the snowpack. So it's basically how much is entering the hydrologic system, so into the soils. And so in black we have our inflow, and so here's our 24,000 event. Blue is our SWI from rain. Orange is our SWI from snowmelt. So we're getting a lot of snowmelt. We have a lot of these snowmelt pulses, probably from other smaller rain on snow events, but we're not seeing it show up in the reservoir. And so what's happening is it's just priming the soil. It's getting everything wet, and it's making sure that basically, because we're coming off of a drought, soil is just kind of absorbing all that water. Until this one, where we had a one-day inflow of basically snow melts about 140,000 acre feet. So that's about 15% of the entire Boise reservoir storages. So that's about 1 million acre feet the 3 reservoir system holds. 15% of that melted in one day. My guess is this time period, probably the whole reservoir volume melted from the snow. Not all of it shows up in the reservoir, but probably 50 to 60% of it does. So a huge event. And so then it just kept getting rowdy from there on out, and we had a lot of, basically a lot of inflow left throughout the rest of the year. And so we can look at that spatially, like where did the water come from? So we're looking at a spatial model, right? So we can see, a lot of the snow came from the Trinities, a lot of upper Twin Springs by the Sawtooths. So you can kind of really get a good estimate of where this water is actually coming from. So we just had a rain on snow event too. So let's look at what happened. So, from what we're looking at, our total precip over the Boise. So we're seeing in this upper kind of right before we kind of cut it off before it hits the Sawtooths. But, we're looking at localized 4 to 5 inches of water in some of these upper basins. 2 to 3 inches in kind of higher elevations. The amount of rain out of this event, so it was definitely, you can see the gradient from west to east. So we're seeing a lot of rain on the western side of the basin, and it kind of cooled off as it got to the eastern side. But we're still seeing, 2+ inches of rain up at Moores. And about, less than an inch of rain in a lot of these lower elevations. But what it did was it really changed the snowpack. So we had, this is a 1-week reporting interval, but most of this change probably happened in 2 or 3 days from all the rain. So we're seeing a huge amount of decrease, so up to 8 inches of SWE lost in a lot of the lower elevations. So that's a lot of water coming off the mountains. And we're seeing, anywhere from 1 to 2 inches up in the upper higher elevations, and it seems like that's about what happened in the storm. So I think this is a pretty good spatial representation of what this storm produced in the Boise River Basin, at least. And so net, we saw a pretty good loss. A lot of the loss was in that 6,000 to 7,000 foot elevation range. And so if we look at the melt, so that was just a change in SWE. But if we look at how much melt occurred, we can see a lot of melt in kind of the Reynolds Creek drainage and Twin Springs here. But overall, we saw about 500,000 acre feet of melt out of this storm. And my guess is a lot of it occurred Sunday and Monday. And so that's half the volume of the reservoir storage system. So a huge rain on snow event produced a lot of melt in the last couple of days. And so we're looking at the Twin Springs gauge. So that's right here on the middle fork of the Boise. And so it's feeding a pretty big area. And so before the storm, it was sitting about 1,000 CFS. Monday, it peaked up to 12 in basically one day. So a huge pulse of water just coming down that river, basically because of that rain on snow event. All right, so just kind of quickly what we do. So we do a lot of real-time modeling. So we can kind of analyze what we've done in the past, kind of do historic runs, but we also do a lot of operational modeling for stakeholders in California, as well as here in Boise. And so we basically run our model every day over these 6 watersheds. So here's the Tuolumne, Merced, San Joaquin, Kings, and the Kauai. So Yosemite's here, Lake Tahoe's up here, Mammoth is right about there. So we have model results at 50 meters. We basically producing these outputs every day. We have updates from the flights. We typically have a 3 to 5 day turnaround for the lidar processing, and then about less than 24-hour model turnaround once we get that update. So we're trying to get information out as quickly as possible to our stakeholders, because usually my phone starts ringing about a day after a flight, and it's like, oh, is the model updated yet? I'm like, no, it's not there yet. Just give us the time. But I think what's really neat about this project is we're working with the California Department of Water Resources for how to visualize this. And so this is actually on a web page that we're working towards. And so we can actually kind of scroll through our model results in real time and interact with it. So you can click on a point and basically pull up the SWE for that particular point through time. And so you can see, how is it melting? So you can kind of compare lower elevations versus higher elevations and things like that. And so it's a really kind of neat visualization tool for where it's melting, where it's not. Yep. Well, that's it. That's all I got.